Today we're going to be talking about linear constrained optimization. And so oftentimes in either research settings or real world applications, there's typically a large incentive to try and get your problem into a linear constrained optimization form. The reason for that is because we can solve these linear constrained optimization problems to global optimality very efficiently. And so we're going to see how we actually go about solving these linear constrained optimization problems in this lecture today. And so the overall layout of what we're going to be discussing today, we're going to start sort of at a high level, what is a linear constrained optimization problem? And then we're going to go into the actual mathematical formulation for the problem. And then sort of re-look at what we saw last time with the first order necessary conditions, applying those specifically to these linear constrained optimization problems. And that's really the foundation for what we'll go into next, which is the Simplex algorithm. And that's one method that we can use to actually solve these. Okay, so linear constrained optimization at a high level, sort of zooming all the way out, what is a linear constrained optimization problem? Well, anytime that you have a linear objective with linear constraints, that gives you what we call a linear program. So linear program, just another name for a linear constrained optimization problem. Typically, it's referred to as a linear program, though. So oftentimes in the real world, right, we don't have these linear objectives or linear constraints. And so that's where we get this sort of incentive to approximate our objectives through these linearized version of the objective, or the same for your constraints. And so the reason for that is because with modern techniques, we can solve these linear constrained optimization problems to global optimality when we have millions of variables and millions of constraints. So it's a pretty powerful tool that we can use here. Okay, so that's the high level, right? Linear constrained optimization, we're just working with these linear objectives, linear constraints. So to actually see how we go about formulating this problem now, we're going to talk about, there's three different main forms that you'll see here for how to write a linear constrained optimization problem. The two that we'll talk about here is first standard form. So standard form represents the objective as C transpose X. So that's a linear objective because the C vector here is just a constant vector, and it's multiplying our design variables here, the X. And then our constraints, we just have this A matrix, so AX less than or equal to B, and we have the constraint that X is greater than or equal to 0. So this is the standard form where we represent the constraints here with this less than or equal to equality. Okay, so if we want to sort of visualize, get a visual representation of this problem here. If we look at the gradient of our objective, the gradient of C transpose X with respect to X is just C. Okay, so that's what we've drawn here is the C vector. We know from calculus, right, that the gradient of the objective is going to be perpendicular to the contour line. So what we're showing here is a contour line of our objective. So this is a line of C transpose X equal to some constant. Okay, and we know that that's going to be perpendicular to the gradient of our objective. So we can look at several different contour lines, and those are just different lines of C transpose X equal to a constant. And you'll notice that they are all perpendicular to this C vector that we've drawn there. Okay, so that's sort of the visual representation of our objective. We can do the same thing for these inequality constraints. Okay, so very similarly, if we have this vector here that we'll call W, and then we look at a line of constant W transpose X. So this is another contour line now where W transpose X is equal to B. We know that that is also going to be perpendicular to the W vector, which is the gradient of that constraint there. And so now we can talk about these half spaces. And half spaces are just represented by these inequality constraints. Okay, so if we have this W transpose X less than B, meaning we're on the left side of this contour line, that's one half space. Okay, and you can think of that as just like the inequality constraint is just dividing the space into two halves. Okay, on the other side, we have the W transpose X greater than B constraint there. So that's another half space on the other side of this constraint. So that's sort of how we visualize the linear constraints in that case. But that was looking at just one inequality constraint. Okay? Oftentimes we're working with many inequality constraints. And when we have several of these constraints and they intersect, we get this region of space, which is our feasible set in this case, which we're denoting by this script x. Okay, so our single inequality constraint formed a half space. When we have an intersection of these inequality constraints, or an intersection of half spaces, that's making up our feasible set. And the cool part about this is that we know that the half spaces are convex sets, so when we're looking at just a single inequality constraint. And we know that the intersection of convex sets also forms a convex set. So that means that this feasible set that we end up with, made from these intersection of half spaces, is going to be convex. Okay, so what does this mean? If you're not familiar with what it means to be a convex set, or maybe just as a refresher here, if we have two sets, we'll call this one set 1, this one set 2. The visual explanation of what it means to be a convex set is just pick any 2 points in this set, draw a line between them, and if any point along that line is still within the set, it's a convex set. Okay, so set 1 here would be a convex set. Set 2 is not going to be a convex set. The reason for that is pick these 2 points, draw a line between them, and you can see that the line leaves the set there. Okay, so that's not a convex set. Now, you might be thinking to yourself here, when you see this, that this set that we've drawn here sort of looks like Baymax from Big Hero 6. And I would say if that's what you're thinking, you're exactly right, because that does look like Baymax from Big Hero 6. Unfortunately, though, Baymax is not convex. So if your problem involves Baymax, you're kind of tough out of luck here, unless it's just focused on Baymax's head, in which case Baymax's head is a convex set. So back to standard form. The main takeaway there was that these convex sets give us the property that our feasible set is convex. Okay, so we know our feasible set is convex. We know that our objective that we're working with is also convex because it's just linear in x. So that means that our problem here is entirely convex. Okay, and so the main takeaway from this result is that if we find a local minimum to this problem, then that is also going to be the global minimum to the problem. Okay, so that's the key result here. And that's why these linear programs are really nice to work with. Okay, and we'll see this theme more as we go forward. So, extending these feasible sets now, there's sort of 3 different cases we want to consider when looking at points in these feasible sets. Okay, so the first one is when we have a point on the interior of the set. A point on the interior of the set is never going to be optimal. The reason for that is if we just look at the gradient of our objective again, so let's say that this is the gradient of our objective C here. We want to minimize the objective, so we're going to move in the negative C direction. So if we're on the interior of the set, we can always improve the objective by just sliding along that negative C vector. So we're always going to be able to improve the objective when we're on the interior of the set. Okay, so that's the first case. The second case is when we have a point on a face. So in this case, we've drawn this point here on the face of this boundary. And points on the face are only going to be optimal in the case that the gradient of the objective C is perpendicular to that face. Okay, because notice what this ends up being. This is just a contour line of our objective, right? Just like what we saw before. So anywhere along that face is a line of C transpose X equal to some constant. So if we were to slide this point along this face here, anywhere we slide it on that face is going to have the same objective. So no point along that face is better than any other. Okay, so in this case, we would have infinite solutions here because there's infinite points that lie along that face. All right, and then the third case that we would work with is when we have a point at a vertex. Okay, so these vertex points are going to turn out to be very important. And that's because that when we have a point at a vertex, depending on the orientation of our C vector here, in this case, that will be the optimal point, because if you move in the negative C direction, you can't improve any further than that point that we have at the vertex. Okay, so the really cool part about linear programs is that we know if they have a unique optimal solution, it's guaranteed to exist at a vertex point. Okay, because that vertex point is a unique point. So if there's a unique solution, it's going to exist at the vertex point. Okay, so we saw standard form. Now for equality form, it's the same exact problem now. We're just changing the inequality constraints into equality constraints. Okay, so what we saw before was the standard form on the left, and then the equality form is now on the right. Okay, so to do this conversion, to get from standard form to equality form, all we want to do, basically, is we just want to change our equality constraints. So we want ax less than or equal to b. We want to get that into a form of ax equal to b. Okay, so how are we going to do this? Well, for these inequality constraints, we can just introduce what's called a slack variable. Okay, so what this is going to look like is we're going to have ax plus s equal to b, where this s is what we call a slack variable, and it's greater than or equal to 0. Okay, so I think it helps to see an example here. So if we have the problem starting with minimize x with x greater than or equal to 1. So if we want to transform this inequality constraint into an equality constraint, it's just going to become x minus s equal to 1. Okay, so you might be saying now, well, why is it a negative sign here when before we had that plus sign? So I think the best way to think about this is just to draw out a number line here and visualize it. And this helps to sort of keep the sign straight. Okay, so if this is our 1 point, we're saying we want x greater than or equal to 1. So we want to be on this side of 1. Okay, so if we have x here, then we satisfy this inequality constraint. And now we're just representing this inequality constraint in a different form. Okay, so we're saying the exact same thing, but this is just our s variable now. So however far or however close x is to 1, we're still representing that same inequality, just now in a hard equality form by subtracting s. That's why we have a negative sign. Okay? You can think about it in the opposite case too. So if instead we had x less than or equal to 1, so now we want our x to lie over here, this is where we're just going to add s on. So we'll have a positive sign for the slack variable. Okay, so that's all we're doing with slack variables. It's just rewriting the inequality constraints into a hard equality constraint. Okay, so that's how we convert between standard form and equality form. The reason that we want to do this is because often we're going to be working primarily in equality form, specifically with the Simplex algorithm. It sort of assumes that we're passing in a problem formulated in the equality form of the problem. Okay, so it's kind of a convention that we're working with, but it's important to know how we shift between the different forms. Yes?
Sorry, going back a little bit, why is it that we're forcing x to be positive? Like, why is that a convention, and also why can't we just not have that?
Yeah, good question. So the question was, why are we enforcing that x has to be positive? So that's another assumption from the Simplex algorithm, that we're sort of working in the positive quadrant here. So we're requiring that x be greater than or equal to 0, similarly to how we're requiring that we pass it in this equality form. So it's just sort of an assumption that we're making and enforcing. And it's basically, if you had an x that you're starting with that's not greater than or equal to 0, you can similarly do a same type of transformation to then get that x to be greater than or equal to 0. Okay, so that's the overall problem formulation. We're primarily going to be focused on equality form as we're moving forward now. And so what we saw last time was this idea of the first order necessary conditions. And we're going to be using these first order necessary conditions to determine when a vertex is optimal and how we're going to transition between these vertice points. Okay? So just sort of as a refresher from last time of what the first order necessary conditions are, we saw that the general case of the Lagrangian for a constrained optimization problem can be written like this. Okay, so we have our objective f of x, g of x here are for the inequality constraints, and h of x are for the equality constraints. Now recall here that the g of x that we're working with, I'll just write this up so we don't forget, g of x here is assumed to be less than or equal to 0. Okay, so that's the inequality sign that we're working with here, where the g of x are less than or equal to constraints. Okay, so if we want to write this now for our specific linear constrained optimization problem in equality form, we have our problem here on the left. So the Lagrangian for this is just going to be C transpose x, which is our objective. Then notice we have this minus mu transpose x. So why do we have the minus sign when up top we had the positive sign? Well, it's because we assumed that g of x was less than or equal to 0, but now we have this x greater than or equal to constraint. So we're just introducing that negative sign to flip the sign of the inequality. Okay, so that's where that negative mu transpose x term comes from. For the equality constraint, the sign of lambda doesn't actually matter, okay? And we'll see the visual interpretation for why that's the case here in a second, but the sign for lambda can be either positive or negative, and then when we actually do the optimization, it'll make up for it in whichever way it needs to be for the optimization to happen. Okay, so only mu has the constraint with this specific form of the sign. Okay, but just keep in mind what the Lagrangian is representing. It's a way to penalize these deviations from the constraint. So if we're not meeting the constraint, we want to penalize that in this Lagrangian objective here. Okay, so the first order necessary conditions, just recapping them here. The first one that we had was feasibility. Okay, I think this one's pretty straightforward. We just have to satisfy the constraints, right? In order for a point to be optimal here, it has to satisfy ax equal to b and x greater than or equal to 0. The next one, dual feasibility, I find that this one's maybe neglected sometimes in people's intuition of why we have this dual feasibility constraint. So I think the best way to keep it straight is through this visual intuition that you want to have behind the dual feasibility constraint. So recall for x greater than or equal to 0, so say this is our constraint here, which it is. So we have this greater than or equal to 0 constraint. With the Lagrangian, we want to introduce this penalty. Okay, so that's the whole idea here, is we want to penalize being infeasible. Okay, so for the x greater than or equal to 0 constraint, we don't want to penalize if we're greater than or equal to 0. That means we're feasible, so we don't want to enforce any penalty there. As soon as we're slightly less than 0, we're saying, let's give infinite penalty now. This is a terrible point. We don't even want to consider this infeasible point. Okay, so that's this infinite step function that we're getting here. But when we're actually going about optimizing this, right, this is not very conducive to set up in an optimization because you have this discontinuous function here with this infinite step. Okay, so instead of that, we introduce this mu transpose x penalty here. And notice, again, we have this negative mu x. So it's just a linear, we're saying we're enforcing this linear penalty now. And we require dual feasibility, which is mu greater than or equal to 0, to enforce the correct direction of this penalty. Right? So it's basically just saying that the slope of this line has to be in the correct direction. Right? If mu was allowed to go sort of into the positive quadrant there, it wouldn't make any sense for the penalty that we're trying to enforce. So that's where this dual feasibility requirement is coming from, is the slope of this mu transpose x line. Okay, and the same picture applies also to complementary slackness, which we're going to see here. And that's the third first order necessary condition. So complementary slackness is saying this element-wise product. So the element-wise product there is just saying either the component of mu or the component of x has to equal 0. Okay, and why this is the case, we'll see again with this picture. So looking at mu transpose x here, we can consider the three different possibilities here. Okay, and recall what we saw last time was we get this infinite step function back by introducing this maximize over the Lagrangian with respect to our mu parameter here. This is how we recover that infinite step function. Okay, and we'll see how this works. So if x is less than 0, meaning we're infeasible, so our point is going to be over here to the left, then this maximize with mu greater than or equal to 0 is saying now we want to make this penalty as large as possible, right? So if we have this line here with the slope that we can control, so mu is the variable that we're controlling, we basically want to crank mu up now as large as possible, and when we do that, we're going to get the infinite step back, right? Because that point was infeasible. So mu here is the parameter that we're varying, and that's how we get the large penalty there for an infeasible point. Now in the other case here, where x is greater than 0, meaning that we're already feasible to start with, we have a similar thing that's going to happen here. Notice that our mu here, so in this case, we're at this point, so the penalty that we're currently receiving is negative, right? But we want to have the maximum penalty possible. So we're again going to crank up the mu, or in this case, we're actually going to decrease mu to increase our penalty here. And the highest penalty that we can receive for this point is going to be 0, okay? Because we have to require that mu is greater than or equal to 0. So, and this makes sense, right? We're already a feasible point. We don't want to be penalizing at all. Okay, and then the last case is just when x is equal to 0, in which case the penalty that we're going to receive is 0. Okay, but in this case, we're at the active constraint. The constraint is active. We're right up against that constraint. And so in this case, x is 0. So what the complementary slackness here is saying is either mu or x is going to be 0. We saw that when x is already feasible, then mu is going to be 0. And when x is active, then mu can be whatever we want it to be, but x is already 0. Okay? So complementary slackness is just saying either the constraint is active or inactive. That's the main takeaway there. Okay, so from that infinite step penalty, right, that maximize with respect to the Lagrange multipliers, we then put that back into our original problem that we started with, which is minimizing with respect to x. Okay, and so that's where the primal form of the problem comes from. And so the last condition that we have here is stationarity, which is this A transpose lambda plus mu equal to c. So where does that come from? That comes from taking the gradient of x, the gradient of our Lagrangian with respect to x. Okay, so when we take that gradient, we just end up with that term and we rearrange it here to get A transpose lambda plus mu equal to c. So this is another way to think about this is saying what we saw last time, that the objective function contours are going to be tangent to each active constraint. So that's another way to think about this stationarity condition. Okay, so for linear programs, the important part about these first order necessary conditions are that they are also sufficient. Okay, so what this means is that in a regular, just a general constrained optimization problem, if you have some point x and it satisfies these first order necessary conditions, it means it could be optimal, but that's not enough to show that it's optimal. Okay, so just because you have some point in a general problem that satisfies these constraints doesn't mean that that point is optimal. So they're not sufficient for a general problem. For a linear program though, if you find a point x and it satisfies these first order necessary conditions, then you know it's the global optimal solution. Okay, so you can say, boom, we're done. We found the optimal if it satisfies these. So it's necessary and sufficient to show optimality. Okay, so that's an important result that we're going to be working with. Okay, so to build up to the simplex algorithm here, these are sort of the key concepts that we need in our toolkit to be able to construct this simplex algorithm. So what we've seen so far, we've seen this idea of feasible sets, equality form, the first order necessary conditions. All that's really left here in our toolkit is this idea of vertex partitions. Okay, so that's what we're going to go into next. So we've seen this idea of vertices already. Vertex partitions are just a way for us to be able to keep track of the indices that are in our x vector as we move throughout these different vertices. Okay, so that's all we're doing here. The important fact that we're going to be working with here is that for our linear programs in equality form, every vertex is going to be uniquely defined by n minus m components of x equal to 0. So when I think when you see that just written up there like that, you're like, okay, but why is that the case? So that's what we're going to go into now. And I think the best way to do that is through an example. So if we have this simple example here, just with two variables, so x1 and x2, we want to minimize x1 subject to this x1 plus x2 equal to 1 constraint. Okay, so what that looks like visually in this x1, x2 space is we just have this single constraint here, the single equality constraint. So we know that the optimal solution has to lie somewhere along this line, this x1 plus x2 equal to 1. Okay, so if we look at the vertices here and where they occur, we have one vertex here at this point, 0, 1. All right? Notice that the first component of x here is 0. The other vertex lies at this point here at the 1, 0 point. Notice that the second component of x is 0 at this point. So in this simple example, right, we just have two variables. So n here is 2. M here, we just have one equality constraint, so m is 1. So we know n minus m is going to be 1. So each vertex is going to be defined by n minus m components of x equal to 0. Okay, so that's one way to look at this. I think this is a simple visual example that we can look at in 2 dimensions. The problems that we're going to be working with, though, have many higher dimensions, right? We could be working with a problem with millions of variables, in which case we're not going to be able to visualize it like this. So I think this is a nice example to sort of get us started, but I think the better interpretation to have of this is through a linear algebra perspective. Yes?
Sorry, can you just go over what n and m are?
Yes, so n is the dimension of our x, so how many variables we have in this problem. So we have x1 and x2. So we have 2 variables, which is n. and then m is the number of equality constraints that we have. So here we have one equality constraint, which is x1 plus x2 equal to 1. And we'll see that here in this, this linear algebra interpretation. So this is another way to look at the exact same fact here that we're working with. So in this case, we've just written out ax equal to b. In this case, we have n equals 5, so we have 5 variables, and we have 3 equality constraints represented by the rows of this A matrix. Okay, so now let's say, for example, that the second and fifth component of x here are 0. All right, so what happens when we do this matrix multiplication is we're going to have this first row of A multiplied by this, the vector of x here, but notice that the second and fifth component are just going to be multiplied by those zeros. So that whole entire second column and the whole entire fifth column, as we carry out this matrix multiplication, are just going to be removed, basically. They're not contributing anything because they're just multiplied by those zeros. So we can equivalently write this same matrix multiplication just in terms of the first, third, and fourth columns of A. Okay? And so what we've actually done here is we've removed n minus m columns out of our A matrix. Okay? So in order to get a unique solution, which means in this case that this A matrix that we have left would be invertible. Okay? So if A here, if this A leftover matrix is invertible, we're going to have a unique solution here. Okay? So I think it helps to see this worked out a bit more. Okay? But this is the idea that we're getting to, is sort of removing these columns of A, and that will give us then hopefully an invertible A matrix. Okay? So that's the direction that we're heading. We'll see a bit more detail here on this partition. Okay, so to remove these columns of A, that's sort of what we're focused on here. We're starting with our x variable here. We're going to be looking at the indices of our x variable. Okay, so we have n indices. So x1 is just the first variable up to xn, so the nth indice there. And we're just going to be keeping track of these indices. Okay, so we're going to do this through what we're going to introduce here is the basis set, and then we're going to introduce the free variable set. Okay, so just 2 different sets, and all we're going to be doing is basically tracking the components of our x. So what is the basis set? The basis set, what this says here is just for an index in the basis, that means that x of that index is going to be greater than or equal to 0. So the xith component is going to be greater than or equal to 0 for it to be in the basis set. Similarly, for it to be in the free set, we just have any index in the free set is defined by xi equal to 0. So we're saying the ith component of x is equal to 0. Okay, so to sort of make this a little more concrete, just looking at that previous example that we saw with that x vector here, the basis set in this case is just going to be 1, 3, and 4. Okay, because we know that the free variable set, the components of x that are equal to 0, is just 2 and 5. Okay, so it's just a way to, we're just partitioning up our x indices and keeping track of them. So a way to keep track of this denotion between this basis and free set, one way I like to think about it is just B for busy. So if you're in the basis set, you're busy. If you're in the free variable set, you're vacant, or you're 0. So we typically call them the basis and free, but just another way to think about it is busy and vacant. Okay? Yes?
Aren't the vacant elements also greater than or equal to 0? Namely, give 0.
Yes, that is true. So you can have, the question was, aren't the vacant elements also greater than or equal to 0, since they are 0? So yes, that is true. You can actually have components in your basis set that are 0, okay, but the free variable set is uniquely defined, meaning all of those components in the free set are going to be 0, okay? But you could have components in your basis that are also 0.
Left side?
The right side is a strict subset of the left side. I don't know if I would think about it as a subset, but just that you know that in your free set, all of the components will be 0. Yeah, I think it'll become maybe clear as we work through this example here. Okay, so going back to that example we saw before here with this, the A matrix we were looking at. So we can write this AX equal to B constraint in terms of just the basis variables here. Okay, so what we saw before, we had this AX on the left side, and then the A basis term here is just plucking out the columns of A corresponding to the basis indices. So that's exactly what we did before. And x basis is just plucking out the components of x that are in our basis. Okay? And so that equality is still a strict equality that ax is equal to a basis x basis. So now, sort of seeing that point from before that if this a basis is invertible, we're going to get a unique solution here, and that unique solution, if it exists, is going to be a vertex point. Okay, so that's sort of that linear algebra interpretation of removing n minus m columns or n minus m components of x from this and setting them equal to 0, then is going to uniquely define this vertex point. Okay, so that's sort of the linear algebra perspective on that same problem. So it's important to keep in mind here, though, sort of a subtlety that every vertex is going to be defined or has an associated partition with it, but not every partition that you get necessarily corresponds to a vertex. Okay, so I think it helps to see an example of when this would not hold here. So if we had the following equality that our A matrix was 1, 2, 0, and 1, 2, 1, and then our x has 3 components here, and we're saying this is equal to 1, 1. Okay, so now say that someone comes to us and says, okay, the basis here is going to be, your basis is 1, 2. Okay, so if we rewrite this now in terms of A basis and X basis, what we end up with is 1, 2, 1, 2. And then multiplied by x1 and x2. Okay, so just taking the elements from our basis here. And we're saying this is equal to 1, 1. But notice what we have here. This A basis that we have is not invertible. Okay, it's not full rank, so we cannot invert this. And this is not going to have a unique solution. So just because somebody gives us a partition here with this basis does not mean that it corresponds to a unique solution at a vertex point. Okay? The other way is true, though. If we do have a vertex point, then it will be defined by some basis partition, and that will have a unique solution here. Okay? But just because somebody gives us this partition doesn't mean it holds. So it's a one-way street here, not a two-way street. Yes?
Sorry, when you write B equals the set of numbers 1, 2, do you mean that your bases are your standard basis 1, 0, 0, and 0, 1, 0?
So the question was, is the basis like the standard basis corresponding to these element vectors?
What does it mean for 2 scalars? Basis.
Yeah, so these are just the indices. You can think about them as the index components of x. So if I say the basis is 1 and 2, that means the basis is x1, x2 here. So you're just indexing into your x vector. Okay, so now we just want to start constructing some of the code that we're going to be using as we build up the simplex algorithm here. Okay, so this is the examples from the book here. And we're working in Julia, but you could just as well do this in any other language you wanted. It's pretty, I think all of the code throughout this is pretty high level, so you could easily translate this to anything else you wanted. But here we're just setting up the linear program here that's just defined by our A matrix, our B and C vectors here. Okay, and then we're going to introduce this getVertex function, which is going to take in a basis here, which you could think about as just a list of integers that we're passing in. And then the linear program here is just what's defined up here. Okay, so the first thing we're going to do is we're just going to read in the A, B, and C that's defined in our linear program. We're going to sort the indices in our basis, because maybe somebody passed them in and they're not already sorted. So we're first going to sort those indices. And then we're going to just extract. This is just taking the columns of A corresponding to our B indices. So we're just pulling out the columns of A that are in our basis and putting those in A basis. And now we're just going to solve for X basis here. So we're just going to do this. This is just AB inverse times B. So that's exactly what we saw before. We're just solving for X basis there. And now we're just going to initialize X to be all zeros. So there's n components here, because there's n components in C. So it's just n zeros that we have. And now we just know the non-zero ones, and I think this sort of gets to your question earlier, is that the non-zero basis components here are going to just be filled in with whatever their corresponding values were from solving that matrix inverse above. And then we're going to return that x vector that we get. So this is just simply taking our linear program that we've defined, getting the vertex associated with it from our partition. And we'll come back to this function later as we build up. So now we've sort of seen all of the different tools that we need in our toolkit to work up to the simplex algorithm. Okay, so now we're going to transition into starting to build the simplex algorithm here. And the simplex algorithm is guaranteed, so it's one way to solve a linear program, and it's guaranteed to solve any feasible and bounded linear program. Okay, and so how the simplex algorithm works at the highest level is it's basically just moving between these vertices in the feasible set, and at each vertice, it's checking the first order necessary conditions, and it's saying, do I satisfy all 4 of the first order necessary conditions? No, then I'm going to move to a new vertex. If it's yes, then I know I found the global optimal point, and it's at that point that I'm currently at. So we're just moving between these vertices in the feasible set. And as we move between those vertices, we're going to use our partition, so our basis and free variables, that's sort of tracking, okay, what vertex am I at right now? And that's basically all we're doing. Okay, so as we go into the details here, don't sort of lose sight of that high-level picture that all we're doing is sort of storing these partitions, and we're going to be moving indices in and out of our partition. That's all that's going on here. Okay, so simplex algorithm, there's 2 phases to it. There's phase 1, which is the initialization phase, and phase 2 is the optimization phase. So in the initialization phase, we're focused on finding a starting initial partition to work with. Okay? From there, we go into the optimization phase, which is how do we now actually find the optimal vertex and do that movement between vertices. Okay? And so we're going to start with phase 2 here, because that's actually where the bulk of this algorithm is inside phase 2. And then we're going to come back to phase 1 and talk about how do we initialize the algorithm. Okay, so starting with phase 2, the optimization phase. What we're focused on here is we just want to move between vertices, right? So we want to move between x and x prime. And we know that as we do this movement, we have to satisfy ax prime equal to b. Okay, so that has to occur. We're assuming that we're starting with some partition given to us. Okay, how we get that partition is going to be part of phase 1, which we'll come back to. But for now, we're assuming we have some partition. So all the optimization phase is we're just choosing an entering index and a leaving index. And we're just going to do this swap. We're just swapping the entering with the leaving index. Okay, so we're just going to trade between our basis and free variables. So one index is going to come over from our free variables, one index is going to leave from our basis. It's just a trade of indices. That's all this optimization phase is. But now we're going to talk about how do we actually choose this index q, this entering index q, and how do we choose the leaving index p. Okay, and so that goes back to our first order necessary conditions here. Okay, so we're going to start with the stationarity condition, and we're just going to rewrite it in terms of our basis variables. So we had our stationarity condition as A transpose lambda plus mu equal to C. So we can just rewrite this now in terms of our partitions here, where we have A transpose basis lambda plus mu basis equal to C basis. Okay, so all we've done is just sort of access the specific components for the basis partition. We can do the same thing for the free variables. Okay, so nothing crazy here. We've just rewritten this in terms of the different components there. So what we know now from complementary slackness is we know that mu b, so for our basis here, we know that this will be, we can choose it to be 0, okay, for our basis. So we have mu b 0 from complementary slackness. And so what we can then do is solve for lambda here. So if we just basically cancel this out here and then solve for lambda from this equation, we're going to get lambda equal to A basis inverse transpose C basis. Okay, and similarly, we could solve for mu of the free variables by just moving this over. Okay, so The good news here is that given some partition, we can solve for lambda and mu. Okay, so this is good news because we saw earlier that if we could solve for our Lagrange multipliers, that allows us to check the first order necessary conditions. So from here, what we want to do is we want to get back to this idea of how do we transition between x to x prime. Okay, that's sort of the question that we have here. And so to think about this, what we're going to introduce is this idea of x basis prime, okay? And we're going to break this down what this means. So if we're currently at some point, some vertex point, x1, x2, x3, let's call it. The actual dimension here doesn't matter. I'm just giving us a concrete example here. And we're going to move to x prime here, which is x1 prime, x2 prime, x3 prime. And say that for this point that we were at, our basis, we had a specific basis here, accessing the components of x. Okay, so what it means to have x basis prime, or x prime basis, is that we're looking at this new x prime point, but using the old basis. So using this basis here for our old point. Okay? And what we know is that we're going to have this swap occur between our basis and our free set. Okay? Where we know that q, we're saying that the q indice is going to come into our basis, okay, and the p indice is going to leave our basis. Okay, so we have this swap that's occurring. So what this means when we're looking at this new point, x prime, using the old basis, this means that the pth component of this is going to equal 0, okay, because that pth component is leaving our basis, so it's going into the free variables, which means here that this x basis prime, the pth component, is 0 because it's now in the free variables. Okay, so that's sort of the idea we want to keep in mind. All we're doing here is basically some indice accounting, okay, just tracking where our indices are going. Okay, so with that idea, we can then rewrite our constraints. So we saw that we had this constraint, right, that ax was equal to b, okay? And we also know that ax prime has to satisfy this constraint as well. So we also have to have ax prime equal to b. And then lastly, we saw that ax equal to b was also equal to a basis, x basis. So that's just sort of summarizing everything we've seen so far. Now what we want to do is we want to be able to write this equality in terms of our p and q indices, so we can sort of track where they're moving. Okay, so we're just going to rewrite this now as ax prime equal to a basis, x basis. So that's just this line here. And now this is going to be a basis times x basis prime. Okay, so this is accounting for the fact that p is leaving. So it's sort of just like a conservation of mass type of term here, where we have what's leaving the system is this p index. What's entering the system is the new q index. So this is the qth column of A times x prime q. Okay, so this is what's leaving our basis. This is what's entering now. Okay, so we're just keeping track of leaving, entering. We know that the pth component here is 0, so that's leaving. We have to keep track of now what's entering through q. Okay, so this is just rewriting this ax prime equality in this form. So now what we can do here is we can solve for x basis prime, because that's what we're interested in. So if we rewrite this now in terms of x basis prime, what we get is we're going to have x basis minus a basis inverse aq xq prime. Okay, so that's just, we basically just took the inverse of this a basis and then moved this over to the other side, and we get this for x basis prime. Okay, so this is, we're getting somewhere here, but we still don't know xq prime. Okay, so how do we solve for xq prime? So in order to do that, we're going to basically do this same exact thing of rewriting the constraint. We're just going to now do it with the objective. Okay, so doing this with the objective now, I'll come over here. So we can now look at C transpose x prime. Okay, so that's the objective of our new point that we're going to be at. So we can equivalently write this just like what we saw as C basis transpose X basis prime. So we have what's leaving here. Now what's entering is going to be C transpose times, and this is Q times X Q prime. Okay, so this is entering now, entering our objective. This is accounting for what's leaving the objective. So just the same exact thing we did over there, now applied to our objective. And so what we can do here is now we can simplify this because we solve for X basis prime on that board. So if we just substitute this in, we're going to get C basis transpose times X basis minus A basis inverse AQ XQ prime plus CQ. This is just CQ since it's a scalar, so there's no transpose here. CQ XQ prime. Okay, so we just plugged in X basis prime. That's all we did in this step. So now we can just go through and start simplifying this. All right, so it's going to give us C basis transpose X basis. Notice this C basis transpose X basis is actually just, this is just C transpose X, right? Because we saw before you can rewrite it in terms of the basis or in terms of the regular variables, because anything not in the basis is just 0. Okay, so that's just this term that we've simplified. Then we're going to have minus C basis transpose A basis inverse AQ XQ prime plus CQ XQ prime. Okay, so now recall from what we saw earlier that we could solve for lambda, and when we solved for lambda, we found that lambda was equal to A basis inverse transpose C basis. Okay, so this A basis inverse transpose C basis is just this term right here with the transpose applied. Okay, so this is just, this term here is just lambda transpose. Okay, so we can just make that substitution now. And so now simplifying this again, we're going to get C transpose X minus lambda transpose AQ XQ prime plus CQ XQ prime. Okay, we're getting somewhere here. We're getting somewhere. So the last simplification that we can make is, recall that we saw from before, I erased it. No, okay, it's up here. So we saw from this here that we have this in terms of the free variables, right? Well, Q is one of our free variables. Okay, so instead of just writing this as all of the indices here, we can rewrite it as just, I'll write it over here. So we're just writing that equation now, but it's in terms of just the Q index. Okay? Okay, so we've just rewritten that same equation, but now just with the Q single variable here, or single index. So if we solve this for this term right here, we're going to get AQ transpose lambda equals CQ minus mu Q. Okay, so this AQ transpose lambda, this is just a scalar term here. So whichever way we do this transpose doesn't actually matter, because so these two basically are equivalent since this is just going to be a scalar here. So A transpose lambda or lambda transpose AQ, they're the same thing. So we can just substitute this in now. Okay, and so simplifying again, we're going to get this C transpose X prime minus C transpose X. So we're just moving this term over in this step. This is equal to what we have here. This is just going to be CQ times XQ prime. And then this should be a negative CQ, right? Because we have this negative sign here. So negative CQ XQ prime plus now mu Q XQ prime. And then finally, we have this term here, plus CQ XQ prime. Okay, we're almost there. Now notice that these two terms are going to cancel out. Okay, so this will cancel out with this. And now we have the final result of C transpose X prime minus C transpose X equal to mu Q XQ prime. Okay, so if you recall, when we started this journey, we were trying to find what xq prime was. How do we choose this xq prime? And so this equation here is very important because it's going to guide us in how we determine what this xq prime is. Okay, so to see sort of the importance of this equation, we'll switch back to the slides here. And so this is the result that we ended up with here. Notice what this is telling us. This is telling us that the objective function here, when we move between x and x prime, the objective function is going to decrease only if this mu q term is negative. Okay, and we want to, that's what we want to do. We want to decrease our objective. We're trying to minimize our objective. So we're looking for negative mu q components here. So in order to move towards optimality, in order to keep sort of improving our objective here, we need to choose an index from our free indices such that mu q is negative. Okay, so we're basically just looking for these negative mu q terms. If all of the components of mu in our free indices, so if all of those components of mu are non-negative, that means that we found a global optimum because we were satisfying dual feasibility and complementary slackness. So we're satisfying all of our first order necessary conditions. So all we have to do is look at, are all of mu v positive or are they all non-negative? And if that's the case, then we know we're at an optimum. Okay, so this is why it's an important result here. This doesn't tell us, though, exactly how we choose our Q index, right? It just sort of gives us some guidance. And so there's a few different entering heuristics that you can use to choose this Q. Okay, so the one that we're going to be using today is the greedy heuristic, which is just choosing the Q that maximally reduces our objective. There's other heuristics out there as well, and you can also use a combination of these heuristics. So this is just something to sort of be aware of. What we're going to be using today is just the greedy heuristic here. Okay, so we're first, recall what we're doing here in this phase 2 of the optimization. We're first choosing the entering index Q. We're then solving for the leaving index P that corresponds with that Q. Okay, so we have one last step here. We now know how we're going to choose our xq prime, but now we need to know how are we choosing our P. So I'm going to erase this part here. Okay, so just rewriting what's covered up on this board is we had that x basis prime was equal to x basis minus a basis inverse aq xq prime. Now we need to know this in terms of the P index that we're working with. Okay, but remember what we saw before was that x basis prime, the pth component of that was 0. Okay, because this is looking at our new x prime point with our old basis, meaning the leaving index P has to be 0. Okay, so we can just rewrite this now. This is going to be x basis in terms of P minus a basis inverse aq, the pth component of that, times xq prime. Okay, so this allows us to now solve for xq prime. Okay, so if we rewrite this now for xq prime, what we get is that xq prime is equal to x basis P divided by a basis inverse aq and the pth component of that. Okay, so notice what's going on here. If in the case where xq prime is equal to 0, that means that this is 0, so this whole term is gone. We just have that the new point would be equal to the old point, right? That's all we're saying in this equation. As we start increasing xq prime, we're going to increase xq prime until one of these new components becomes 0. So until P leaves the basis. Okay, that's why it's the leaving index. So this right here is called the minimum ratio. So we're using the minimum ratio test here with this P, the P components here. So we're basically going to increase xq prime up until the first component P leaves the basis. Okay, so we're just going to keep increasing xq prime until we get something that leaves. So roughly how the algorithm is going to work here is we're going to kind of have these two for loops. On the outer for loop, right, we're going over all of the q's in the free variables. So we're going to iterate through all of the q in the free variables. For each of those q, we're going to look at the p in the basis. Okay, so for the first component of q in our free, we're going to look at now the first component of p. We're going to compute this ratio as we go through all of these different p components, and we're going to select the minimum ratio. Why the minimum? That's because that's the first one that's going to give us a leaving index. Okay? So we're going through all of the q's in the outer for loop. Then on the inner for loop, we're looking for that p pair, that pq pair here. Once we find it, we then store that pq pair, and then we look at now our objective over here, which q is giving us the maximum decrement. So we store all these pq pairs, and then for each of those pq pairs, we're computing the objective, taking the one that gives us the maximum decrement. Okay, and we're going to see this all in the code, but this is just sort of the layout here that we have of what's happening. We're just doing these, it all boils down to these two for loops, and all this is telling us is how do we do that swap between q and p. Okay, so I think the best way to sort of see this all now put together is through an actual example here. So again, we're working in this equality form. Let's say that our A, B, and C values are given by these matrices and vectors. And let's say that we have some initial basis that we're saying is 3, 4. In the next phase, we're actually going to have to solve for this, but right now, we're just giving it to us, okay? So how this is going to work in the code is we're first going to enter into this minimize LP function. The exclamation mark here is Julia convention, sort of denoting that we are going to be modifying the arguments that are passed in. So the basis here will be changing in this function. Okay, so we're just going to do, in this minimize LP function, we're just going to enter into this while loop, and we're going to continue to call step LP here until we get this done equal to true. So done equals to true means that we found the global optimum. Okay, so we're just going to continue calling step LP here. So we're going to enter step LP now. And so the first part of this, we are just reading in the A, B, and C like before. N is just the second component here of A, because A is m by n. And then we're sorting the B indices like before. So now we're going to continue on. We've just now read in the free indices as well. So that set difference is just taking the set difference here between the n components and whatever is in B. So this set difference is then just taking whatever is not in B, put that into our free indices, okay? And then we're just accessing AB and AV there, okay? So we solve for x basis like before. So that x basis here, A basis is going to be the identity matrix here, because that just comes from 3, 4, so the third and fourth columns of A form our A basis. Then our B term here is just 9, 2, so that gives us 9, 2 for x basis. Okay, C basis is just going to be the third and fourth components of C, so that's 0, 0 up there. And now we can solve for lambda and mu from the equations that we saw on the board here. So lambda is just A basis inverse transpose. So A basis we already saw, C basis we saw, it's just 0, 0. And yeah, we saw that we can compute the Lagrange multipliers here using these equations. So that's just what we're going to do. So for mu v as well, we can compute mu v. And notice here we have C of the free variables, so the first and second components now of C, minus the first and second columns of A is what's making up this matrix, and then times the lambda that we just solved for. Okay, so now here's where that outer for loop starts. This is that outer for loop that I was talking about here, where we're going to go through all of the Q indices in our free variables. Okay, so we're going to iterate through all of the components of mu free, which are the free components. And what we're looking for here is the maximum decrement in our objective. Okay, we're using that greedy heuristic here to guide us. So as we go through each of these components here, we're checking first, is mu vi less than 0? Why do we care if it's less than 0? Remember, that's the only way that we get a decrement in the objective. So we're only going to look at these components of mu that are less than 0. So in this case, we're looking at this first component here, which is 3. It's not less than 0, so we're just going to continue past that if statement and go back up to the top of our for loop. Now we're going to look at the next component of mu. We see that that's -1, so it is less than 0, so we're going to enter into this if statement. We're then going to run this edge transition. Okay, so this is looking for that PQ pair now. So we've gotten our Q. We know that our Q is going to give us a decrement in our objective. Now we're trying to find the P that goes along with our Q. So we're going to run this edge transition function here, which will find us the P, the PQ pair, and also the XQ prime value through the minimum ratio test. So that's what we're going to enter into now. We'll save our spot in that step LP function as we run this edge transition. Okay, so we're now up here in edge transition. These are the components that we're working with. Our basis is still 3, 4. The Q index that we've passed in here is 2, because that's where we were in that previous for loop. And then n here is just 2 as well. So we're going to compute the n indices like before. Those are just our free indices. And then everything else is similar to what we've done, except for this d term. So d here is the denominator in that minimum ratio. Okay, so this is just the denominator term, the inside of these parentheses. We haven't taken the pth component of it yet, but we're just computing the denominator here. Okay, and so what we've done is we've taken a basis, the inverse of that, since we're using this / operator, and then we've taken the columns of A corresponding to the free indices and the qth component. Okay, so here q is 2, so the second component of n indices is also 2, so we're taking the second column of A. Okay, and that's where this 1, 2 comes from, the second column of A. Okay, so we solve for that denominator term, and now we're going to enter into the second for loop. So this is that inner for loop now where we're trying to find the P pair that's corresponding to it. Okay, so inside this inner for loop now, we check, is d greater than 0? Why do we care if it's greater than 0? Well, we're going to be dividing by it, so we don't want it to be 0 here. We then compute this value, so that's what the v is for value here, where it's just this ratio now. So just xb of the ith component divided by di, so the denominator component. We're going to check, is that value less than the smallest xq prime that I've seen so far, which we initialize it to infinity, so yes, it is. So we're going to store that value here, where value was, it's just 9 here because it was this first component of x basis divided by the first component of di, okay? And so we saw that it was less than that, so we stored p and xq prime, and now we're going to come back up to the for loop because we need to go through the rest of the d components. So now we're back up at the top of the for loop. We're checking now, is the second component, so 2 over here, of d, is that greater than 0? Yes, it is. Let's compute the value, which is the second component of x basis, which is 2, divided by the second component of d, which is also 2. So we get 1 for our value here. Is the value less than the best xq prime we've seen so far? Yes, it is. Remember, we're looking for the minimum ratio here. That's what we're doing inside this for loop. So we then finish this for loop now because that was the last component of d. And so that means we found the minimum xq prime here, the corresponding p. So now we can return that p xq prime back to our step LP function. Okay, so we're almost done here. So we return this back to our step LP. Here now we have this p xq prime and the q, so we have the p-q pair here for this. Now we're looking, is this decrement, so is this mu v of I times xi prime, is that less than delta, which is the largest decrement in our objective that we've seen so far? And remember, we want to minimize, so we want a large negative value. So we check, is that less than delta? If it is, which in this case it's -1, which is less than infinity, so yes, we're going to store that. We update the PQ XQ prime pair that we've seen. And since we only had 2 components here, we're done with this for loop now. Okay, so we found our valid swap here. We found the PQ, the entering and exiting node or indice here that's going to occur. Now we just need to sort of check some optimality conditions. Okay, so we first check, is Q equal to 0? What this means is that we would have made it through this entire for loop, okay, since we initialized Q to be 0, we made it through this entire for loop without having any mu vi terms less than 0, meaning all of our mu v's are greater than 0, and we know that when we saw that, that meant that we were at a global optimum, okay, by the dual feasibility constraint. Okay? In this case, we don't satisfy this, so we have not found the global optimum. We're going to continue. We're then going to check, is x cubed prime infinity? Now, what this means is that we went through this for loop. Q was not 0, okay, meaning that Q had changed. We had run some edge transition here, but x cubed prime has continued to increase or has blown up to infinity, in which case we have an unbounded problem. So we can error out here that the problem is unbounded. Okay, that's also not the case for us, so we can continue on. Now we're just doing this basically swap here, so we're looking for the first component, so B indices of P, so the second component of B indices, which is 4. We're trying to find the first component of B, the original basis. That's just going to be the second component as well. So we're just doing this swap because remember we sorted B. So we have to make up for the fact that we now have a different ordering than what was passed in. So that's all that line is doing. And now we actually do the swap here, where we're saying the second component of B, it was 4, so the fourth index, it's now becoming 2, because that's the swap that we found. So we're just doing that swap now to update our basis partition here. And then finally, we return the basis that we found with a false, since it wasn't the optimal basis. Okay, and so that was one whole iteration of the step LP function here. So we would now return back to our minimize LP, and we have our new basis here with done equal to false. So we would now run this again in step LP. We're not going to go through that for time, but you're welcome to work through it out on your own by hand if you want practice doing this. And the solution that you'll find is that in this next iteration, so if you do one more iteration of this, you'll find that mu v, you can see all of the components of mu v there are positive. So we know that we have now found the global optimum. So we would return on one more iteration of this, and the basis that we would find is 2, 3 with the optimal x point there as well. So you're welcome to try that out on your own and see if you get the optimal solution. Okay, so that was an example of phase 2. So the functions that we've seen so far are these first 4. The last function that we have to finish the simplex algorithm is this minimize LP function, okay, and that's concerned with the initialization phase. But what I think is pretty cool is that the entire phase 2 optimization phase can be done in like roughly 100 lines of code here. So just these functions are capable of handling these extremely large problems and solving them to global optimality. So I think that's just something that's pretty cool, that you have this much power in this small amount of code. Okay, so we're going to switch over now to talk about phase 1. How do we actually get this initial starting vertex here? Okay, and yeah, so what we just saw was phase 2, where we're finding the optimal vertex. Now we're going to be focused on how do we find a feasible starting vertex to work with. Okay, and so as it turns out, identifying these initial partitions that correspond to vertices, that's actually going to involve solving another linear program. So what you might be thinking now is, well, wait a second, you're telling me that in order to solve a linear program, I have to first solve a linear program. Don't we enter this sort of circular loop here and we can never solve it? So the answer is no, and we're going to see why. But yeah, our goal here is just we want to find that initial partition, okay? So in order to do this, we're introducing this auxiliary linear program that we're going to be working with, okay? And so we're introducing these variables z here. The goal of this auxiliary linear program, so this is not equivalent to the original linear program that we're interested in. This is just focused on getting us that initial starting vertex. Okay, so we're introducing these z variables, and our goal here is that if we've truly solved this first one and it's a feasible problem, the z's should be 0, okay? So we want to minimize the z's subject to this ax plus zz term here equal to b. We'll talk about what this z matrix is here in a second. Then we also have this constraint that x in z is greater than or equal to 0. Okay, so what is this z matrix? This z matrix is just a diagonal matrix here where it's a positive 1 on the diagonal if the bi term is greater than or equal to 0, and it's negative 1 otherwise. Okay, so I think when you see this, you might be like, okay, I don't really understand like how this is helping us at all. Okay, and you might have these two questions here. One is, don't we still have the problem of finding that initial partition? How do we know a partition for this problem? So I think that's a valid question. The next one is, why are we defining Z in this way? Why not just make it a diagonal matrix? So we're going to answer both of these questions here. Starting with the second one, why is Z defined like this? So consider the constraint here if we pull it out and write it as AX plus ZZ equal to B. Consider the case here where X is equal to 0. So what we're going to have is just ZZ equal to B. Okay, so in order to satisfy this constraint, we would need some more freedom on our Z variable, because right now we've constrained Z to be greater than or equal to 0. The B terms, though, they can be negative. So if we don't have this Z matrix here with the negative sign, then we could end up with a case where we can't satisfy this constraint. So that's why we're bringing in this Z matrix to give us that additional degree of freedom in controlling the sign of the Z variables. Okay? So that's what this Z matrix is doing, is just allowing us to satisfy this ZZ equal to B. Okay? So it comes from the fact that we require Z to be greater than or equal to 0, so we're introducing this sign degree of freedom here. So that's answering the second question, why is Z defined like that? Now how about the first question? Don't we still have this problem? How do we know an initial partition for this? Well, we can look at, again, if we sort of look at this stacked vector of xz here, if we write it out, we have n components of x, those are our n variables, and then we have m z variables here. So in the case where x is equal to 0, notice what we have here. We have all zeros for x components, and then we have our z variables. Now this is actually a valid partition to the problem. Okay, so our basis here would be n plus 1. It's n plus 1 because we have n components, so just the next component, the first z component, is n plus 1, that's the index, up to n plus m, that's the last component of z, the last index. So that's our basis here, and then we can just initialize that zj is equal to the absolute value of bj. And this would give us an initial partition because it satisfies our axzz equal to b constraint. We have z greater than or equal to 0 here, so all of our constraints are satisfied, and so we can just pass this initial partition to the solver here with this linear program, and if it's a feasible problem, it should zero out all the z's, and what is returned to us now is an initial partition for the original problem that we were interested in. Okay, so this is just sort of a middle step that we're taking to solve the original problem that we want to. Okay, so I think it helps to sort of see the whole pipeline laid out here. And this statement is just saying that the partition that we get by solving this auxiliary linear program will produce a feasible design point, meaning it will satisfy AX equal to B because it also has to respect those constraints. If the Z variables, this is the same thing we just said, so if the Z variables that are returned are not zeroed out, that means that the original problem is not feasible. So we can just sort of stop right there. Okay, so now looking at this entire pipeline laid out, this is going to be the new form of the problem that we're working with. Okay, so we see this sort of transition from this was the original form of the problem. We wanted to get to this, this is the new form that we're getting to, and we're doing it through this auxiliary linear program. Okay, so I think what you might be sort of thinking now is why does Z still show up in our final form over here? Why are we keeping those Z variables around? If we know they've been zeroed out, aren't they no longer important to us? Does anyone have an idea of why we might want to keep those Z variables around? Yeah.
As initial values for the second part of V set?
Yeah, I think, so you said as sort of initial values. Yeah, I think that's pretty close. Basically, right, they might be zeroed out, or they will be zeroed out, but the partition that's returned from the initial solution to that problem might still have those components. So it might have indices corresponding to Z in that partition that's returned, even though they're 0, because we just require that our X basis terms are greater than or equal to 0, going back to your original question. So the Z components, the Z indices, might still be in that basis that's solved for. And so that's why we need to keep them around. So it's kind of a nuanced point that they're going to be zeroed out, but we still need them because the indices are important to us for that partition. Yeah.
How exactly does this return partition?
Yeah, so remember when we called that minimize LP function? What was returned from that was the basis, the partition. So we're updating that basis as we go. So the same thing when we solve that auxiliary linear program, we'll be updating that basis. And so whatever basis is returned from there will satisfy our AX equal to B constraints. Yep. Okay, so now final step here in this last minimize LP function, which is sort of putting everything together here with phase 1 and phase 2. So everything that we're doing at the top is sort of like what we've seen before, except now we're just introducing the auxiliary variable z here. We're setting up this matrix. So this line is just a one-line for loop that says for each component in B here, basically just check is that j, so for each j in this B, is j greater than or equal to 0? If it is, then it's a 1. Otherwise, it's negative 1. Okay, so that's just setting up the z how we saw down there. And now we're building this initial linear program here that we're going to solve. So A prime here is just combining the A and Z matrices, just like down here. Okay, B prime is just like before. And then C prime is just this objective here where we have zeros and ones. And the Z was just initialized to be ones here. Okay, so then we're constructing that linear program. We're going to set up our partition here, which is what we saw. It's just n plus 1 to n plus m. So this collect is just collecting the range from 1 to m and then adding it on to n to get n plus 1 to n plus m. So that's our valid partition. We know that will always be a valid partition. And then we're going to call minimize LP on that. Okay, so that will then modify our basis, and the basis that will be returned will be a starting basis, an initial basis for the original problem. Okay, but first we need to check here, are any of the components of B, so this is looking at any of the indices greater than n, those indices greater than n correspond to the Z values, so are any of those Z not 0? That's what this line is asking. Are any of the Z's not zeroed out? If that's the case, then we know it's an infeasible problem and we can stop right there without solving any further. Okay? If it's not the case that it's infeasible, then we know, okay, we have a valid partition to start our other problem that we want to get to. Okay, so now this is the same problem here, just including the Z variables. Okay? And we need to do that because their indices could be in that partition. So now we set up the final problem here where this A prime prime matrix is just this matrix here. B prime prime is just this vector here, and then C prime prime is just this vector here. Okay? So now we can pass that in where the B partition now, this basis partition, is just what was returned from this function. Okay? So that basis that was returned from our initial auxiliary linear program becomes now our new basis here. And so we can solve this and then call our get return, or our get vertex here, which we will return the actual x. And notice we only take the first n components of that because those are the actual x values that we have. And so that is the entire simplex algorithm, both phase 1 and phase 2 all put together now. And so I know that was a lot of steps and we're almost out of time here. So I think the main takeaway from this is that, yes, there were a lot of steps that went into this simplex algorithm, but they all sort of relied on that foundation of the first order necessary conditions. Okay, so that's sort of the foundation of all of this. And as we went through, we were just doing this indice accounting where we're swapping these indices and checking if any of the first, or checking if all of the first order necessary conditions were satisfied. So that's phase 1 and phase 2 of the simplex algorithm. I'll wrap it up here just with a quick summary. So what we saw was these linear programs at the highest level, right? They're just linear objective. So we have a linear objective, linear constraints. That gives us this linear program. We saw that the simplex algorithm could globally optimize these problems when we have extremely high dimensional variables that we're working with. We can still do it in an efficient manner, all relying on those first order necessary conditions. The part that we did get to, but that we'll get to next time, is on dual certificates, which will allow us to sort of check our solution that's returned here. So I hope that was useful. I hope each of those jumps that we made in each of those steps made sense to you. And I hope that you've seen that the linear programming is a pretty powerful tool when we are able to solve it with this simplex algorithm. So thank you all for listening. I'm happy to take any questions that you have now. Offline. Thank you.